Okay, so last time we had almost finished our discussion of Sumerian Babylonian math. I think the thing I did near the very end of class focused on some of these like approximations. So, for instance, um, the writing out of the approximation of square root of 2 in the Babylonian sexagesimal system. And so that is just one impressive thing due to Babylonian math. Another thing, before moving on to the Greeks, I wanted to read an example here and go through it. So this is another example of Babylonian math. So this is directly from the textbook here. Let me focus. Okay. So this is from a Babylonian clay tablet titled AO8862. And so this is from apparently about the same time as the Rhind Papyrus that we covered when we talked about Egyptian math. And so here's just verbatim what this tablet contains. So length, width. I have multiplied the length and the width, thus obtaining the area. Then I added to the area the excess of the length over the width. 183 was the result. Moreover, I have added the length and the width, 27. Required length, width, and area. Okay, 27 and 183, the sums. 15 the length, 180 the area, 12 the width. Okay, one follows this method. Okay, 27 plus 183 is 210. 22 plus 27 is 29. Take 1/2 of 29. This gives 14 and a half. 14 and a half times 14 and a half is 210 and 1/4. 210 and 1/4 minus 210 is 1/4. The square root of 1/4 is 1/2. 14 and 1/2 plus 1/2 is 15, the length. 14 and 1/2 minus 1/2 is 14, the width. Subtract 2, which has been added to 27 from 14, the width. 12 is the actual width. I have multiplied the length 15 by the width 12. 15 times 12 is 180, the area. 15 minus 12 is 3. 180 plus 3 is 183. Okay. So what is going on here? What is this? So this is a description of a problem and a method of solution here that is, of course, this is a special case. The way that this works out, of course, depends on these numbers, but there's a general method here, okay? And the idea is that this clay tablet is supposed to be showing a general method that can be applied to these numbers, though, of course, this is done via special cases. And this is the common approach in ancient math. And it wasn't until the Greeks that the notion of proving something or doing something generally was set forth to get rid of this need of doing endless amounts of these special cases. So what is it that's actually going on here? What is even being asked? Okay, so what is going on is actually pretty impressive because what's going on is that there's basically a problem statement. So the problem is to find a solution for these two equations. So x times y plus x minus y is 183, and x plus y is 27. So this is what's being asked. So if we flip over to the page here, this first paragraph is the description. Length and width. I've multiplied the length and the width, thus obtaining the area. Then I added to the area the excess of the length over the width, and 183 was the result. That sentence, so that sentence is this equation. So I computed the area, length times width, x times y, and then I added to it the excess of length over width, with the convention that x is the larger of the two. Right, and so the result when I do that is 183. That's what that first sentence is saying. Okay, so then the second sentence says, moreover, I have added the length and the width, and I got 27. Okay, required length, width, and area. Okay, so x plus y is 27. So I have two unknown quantities, a length and a width. Okay, of course, if I don't know the length or width, then I don't know the area. So this is two equations, xy plus x minus y is equal to 183, and x plus y is equal to 27. So two equations and two unknowns. The problem is to solve for x and y. Okay, so this Scribes method gives us a solution of x is equal to 15 and y is equal to 12. You could check that that in fact works for both of these. Okay, so here's the method that the scribe uses. So just going line by line. Okay, so this method of 27 plus 183 is 210. What did the scribe do there? What the scribe did there is adding these two equations, right? So adding these two equations, I add the left-hand side. So I have x times y plus x minus y, okay, plus x plus y, right? So whatever that is, that must be 183 plus 27, which is 210. Now, if I simplify this algebraically, okay, this simplifies as x times y plus 2. Okay, so the y's cancel. This is x here. I can write this out real quick. All right, so this is x, y plus x minus y plus x plus y, right? And so this is supposed to be equal to 183 plus 27. And so on the left, the y's cancel, and I am left with x, y, plus x is plus 2x. And that's equal to 183 plus 27, which is 210. Factoring an x out here, this leaves me with x times y plus 2 is equal to 210. Okay. Okay. And so, going back to what the scribe wrote, that's this step. Saying that now I'm going to separate out this method, or this quantity here, is me just defining. This is me saying let y prime be y plus 2. Then what does this equation become? This equation becomes x times y prime is equal to 210. Okay, just letting y prime be y plus 2. Okay, going back to our description of what the scribe is doing. So, on the other hand, adding the factors of 210, right, what do you get? Well, here you would get x plus y prime, right, is x plus y plus 2, and that has to be equal to 29. Okay, and why does that have to be equal to 29? Well, y prime is y plus 2, right, and I know that x plus y is 27, so if x plus y is 27, right, then this is 27 plus 2, so that's 29. So x plus y prime is 29. Okay. Thus, 1/2 of x plus y prime is 1/2 of 29, which is 14.5. And thus, x squared plus 2xy prime plus y prime squared over 4 is 14.5 squared. Going back to the previous page, this is what the scribe is doing here when he's squaring 14 1/2. So, going back to the computation here. So what's going on is that we have x plus y prime is found to be, since y prime is y plus 2, this is x plus y plus 2. And x plus y, the two equations we started with were xy plus x minus y is equal to 183. And the second equation was x plus y is equal to 27. Okay, so x plus y, oh, I'm off page. So here's my two equations I started with. These are the equations that I'm solving for x and y. Okay, this is my problem that's being solved here. Okay, x plus y is 27, so then x plus y prime, since y prime is y plus 2, this is x plus y plus 2, so this is 27 plus 2, which is 29. Okay, all right. Thus, 1 half of this quantity, 1 half of x plus y prime, is 1 half times 29, which is 14 and a half to use mixed numbers, right? We're using mixed numbers here because we're just verbatim translating from the tablet here, and 14 and a half is what we get here. 1 half of 29, 14 and a half. And then next, I consider squaring this. So I consider squaring this. So I have 1 half times x plus y prime all squared. Whatever that is 14 and 1 half squared. Okay. But what is this? Okay. And why is the scribe doing this method? So the scribe is doing this method as we'll see, the scribe is doing this method as a way of being able to nicely factor what results as a square. Okay. So this is if you remember completing the square from algebra, this is a related thing that's going on here. So the scribe squares this, but algebraically, what is this? This is squaring the 1 half is 1/4. So that's 1/4 times, squaring this, of course I have to FOIL this out, so this is x squared plus 2xy prime plus y prime squared. All right, so it's 1/4, or that all over 4. Squaring 14 and 1 half, of course, is, so the scribe does this and gets, so the scribe gets 210 and 1/4. Okay, so that's what the scribe was doing when they wrote this out. Okay, so then next, right, what is noticed is the following. So I want to keep that on the page. So what is noticed is the following. Okay, so here I want to keep this xy prime being equal to 210 here on the page. So then notice that 210 and 1/4 minus 210 is just 1/4. Why would I think to do this? Algebraically, this is me taking, right, this is equal to x squared plus 2xy prime plus y prime squared over 4. It's taking that, right, and subtracting from it, since 210 is equal to xy prime, xy prime. Okay. Now, of course, 210 and 1/4 minus 210 is just 1/4. So that's nice enough. But this simplifies. How does this simplify? So if I want to get a common denominator here, I could get a common denominator of 4 and then have 4 multiplying xy prime. When I do that, though, here I would have x squared plus 2xy prime plus y prime squared minus 4xy prime. So this becomes x squared minus 2xy prime plus y prime squared all over 4. Why would the scribe do this? Because now this nicely factors, right? This is also a square. This is actually 1 half times x minus y prime squared. Okay. And so the thing that the scribe says next is the square root of 1/4 is 1 half. So taking the square root of both sides, I get that 1 half is equal to x minus y prime over 2. Okay. Well, then what? So how do I get x and y prime from this? Once I have this together with the other constraints that I've gotten up here, how do I actually solve for x and y prime here? So then I want to add and subtract these two things. 1 half x plus y prime, right, and 1 half x minus y prime. And I want to do 1 half x plus y prime minus 1 half x minus y prime. But when I do that, what do I get? So this we saw 1/2 x plus y prime is 14 and a half. And I'm adding to that 1/2 x minus y prime, which is 1/2. So I have 14 and 1/2 plus 1/2, that's 15. Right? And I have 1/2 x plus y prime minus 1/2 x minus y prime, which is 14 and 1/2 minus 1/2, which is 14. But what are these? 1/2 x plus y prime plus 1/2 x minus y prime. 1/2 x, 1/2 x, so that gives me x. 1/2 y prime minus 1/2 y prime, those cancel. This is x, right? Similarly, 1/2 x and minus 1/2 x, that cancels. 1/2 y prime minus 1/2 minus y prime, that's y prime. Of course, my goal wasn't to solve this for x and y prime, it was to solve it for x and y. But what is y prime? Y prime is y plus 2. So we have y plus 2 is equal to 14. So what is y? 12. So we get the solution, x is equal to 15, y is equal to 12. Okay, and that is the process that this Babylonian scribe used. Now, this is not the only solution. There's another solution. Okay, so there's another solution to this. The other solution is, so x equals 14 and y equals 13 is another solution. But the scribe didn't write that. Why? Okay, in fact, this is the only other solution. Why did the scribe not write this? To notice this, one would have to be able to take the negative root from the square root of 1/4. Okay. So, negative numbers weren't a thing for the Babylonians. So, considering the square root of 1/4 is plus or minus 1/2, was not something that was considered. So, in fact, if they actually considered this, they would have noticed that there's another solution that arises here. Okay. All right. So he didn't know how to take the negative square root of 1/4, and so that kept them from finding this other solution. But as you can see, that's a very this is a very sophisticated method for going on, or for going about this problem. And it would be if I just unleashed you on this description without thinking about it. Let me bring it into focus here. Okay, without thinking, without really spending a lot of time trying to figure out what's going on here, it can be very hard to understand why this works or what's happening. But the second that we put this into this more formal algebraic setting of where I restate the problem as solving a simultaneous system of equations and two unknowns, and we proceed like this, then you see the power of doing this generally. And in fact, you could replicate this for different problems, right? That's the idea here. Okay, so that's what was going on. So then it might not be that shocking, since they could handle something like that. It might not be that shocking to find out that there's a lot of other types of equations that they could solve, since essentially what they were doing there was solving some quadratic things, right? So then, what other sorts of equations could the Babylonians solve? Well, they could solve equations, so linear equations, ax equals b, they could solve. They could solve x squared plus or minus ax is equal to b. Okay, they could solve for cubed roots. So x cubed is equal to a. They could solve for particular cubics like this. X squared times x plus 1 is equal to a. They could actually also solve some simultaneous systems of equations. So they could solve systems. Here, that sounds. They could also solve systems like x plus or minus y is equal to a, xy is equal to b. Okay, they could solve a system x plus or minus y is equal to a, x squared plus y squared is equal to b. And they could also solve a system of equations that looks like this. So x cubed times the square root of x squared plus y squared is equal to, so this is a particular one that was actually solved. So this is 3.2 million, okay, and xy is equal to 1200. Okay, so this one in particular, the reason why I list out these numbers in particular is actually this was done in what's called the Susa Tablet. Okay. So this is pretty advanced algebraic machinery for, considering that, like I said, many of these clay tablets, right, are some of, this is done, almost 4,000 years ago. Some of this stuff. The later Babylonian stuff was a little bit newer, but still, you're talking about, mathematics that's at least like 3,000-ish years old. So this is a pretty advanced algebraic machinery for then. What else did the Babylonians know, put in modern notation? So Babylonians also knew some of your familiar formulas for some simple algebraic, like quadratic expressions. So Babylonians also knew, for instance, difference of squares. So they knew that if you have a difference of squares, a squared minus b squared, this could be expressed as a plus b, a minus b. So they were very aware of this. They also knew, of course, how to expand a square in the usual way. A plus b squared is a squared plus 2ab plus b squared. You can see that they knew that from this example that we just did earlier. Okay. Here's an example. So Babylonians constructed what are called ziggurats, okay, which if you've never seen them, so ziggurats are typically used as an example of like the prototypical, Mesopotamian structure because they're very impressive. They were these large, they were pyramid shaped, but they had levels. So if you just Google like a ziggurat, you can see a lot of pictures of them. The Hanging Gardens of Babylon are typically depicted, whether or not they existed. The Hanging Gardens of Babylon are typically depicted as a ziggurat-like structure. So these ziggurats were, I would explain it as they're sloped. The sides were sloped up until a point which was leveled off, and then there could be other levels on top of that tapered off toward the top. So they were almost kind of sort of like pyramids in shape, but they were definitely different than pyramids. Some ziggurats were just had essentially like one platform. They were just one big building. So anyway, the point is that because ziggurats had these levels, that they had these platforms that were easy to compute the volume of. So if you had these ziggurats had a single story consisted of, say, a square platform. And we'll say that, we have normalized this in such a way that this square platform is of size 1 by m by m. Okay. Then the volume of an entire ziggurat with base length, say n, is 1 by n plus 1 by, say, n minus 1 by n minus 1. If we're tapering off 1 at a time here. Okay, and so on, all the way down. So we do this 1 at a time, all the way down to 1 by 2 by 2, and 1 by 1 by 1, right, is the top. Okay. So this would be the volume of a whole ziggurat. So here's my base, and then I'm tapering off 1 story up here, and so on. Okay, so this was me computing the volume of a ziggurat with this base. But what is this, right? So I'm adding the volume of each story individually, and they're sitting on top of each other. So what is this? If we just go through, of course, the fact that I have a 1 here, this is n times n, this is n minus 1 times n minus 1. What is this, right? So this is rewriting it backwards. So this is 1 squared plus 2 squared plus 3 squared all the way up to n minus 1 squared plus n squared. Okay, written in modern sum notation, right? We can maybe make this more convenient. Right, you could say this is the sum from, say, k equals 1 to n of k squared, right? Okay, so this sum computed the volume of a ziggurat, and the Babylonians knew that there was a shortcut for this sum. So the Babylonians knew the shortcut formula. Okay. And so if you've ever had any course that involved basic basic proofs, this is the stuff that you start with because it's an easy way to use induction, right? Mathematical induction proves some of these facts pretty quickly, and it's very straightforward. Of course, the Babylonians didn't do that, but they knew this shortcut formula anyway. So what is this shortcut formula? Well, to compute this sum, you don't actually have to brute force compute this sum. What you could do instead is notice that this sum is actually equal to n times n plus 1 times 2n plus 1, all divided by 6. So you could square each of these things and add them together, or you could just do this quick multiplication. It will do the same thing. You can try it for a few. If you wanted to try this for let n be equal to 6, try to add all those and then just do it this way. You'll see you get the same answer. So Babylonians knew this shortcut formula. Okay. All right. One more thing I wanted to mention about Babylonians, and then that will be it, and I'll move on to discuss the beginning of Greek math. Okay, and so one last thing, and I've saved it for last because this is a thing that gets mentioned a lot. And it's that the thing that we call the Pythagorean Theorem was known much earlier than the time of Pythagoras. So it was certainly known to the Babylonians. In fact, they showed a very nice fact about what are called Pythagorean triples. So it wasn't just that they knew the relationship between right triangles and the sums of squares of the side lengths. So they didn't just know about it in terms of triangles. They also knew about it from more like a number theory perspective of understanding these what are called Pythagorean triples. So triples of numbers that form a right triangle. Okay, or the side lengths of a right triangle. And so this is amazing that it was known this early. Of course, it wasn't proven by the Babylonians. They just knew it through example and empirically from actually dealing with right triangles. So it wasn't until the Greeks that these things were proven. I know that I keep mentioning that, but it's an important distinction. But the Babylonians certainly knew about it and knew a lot about the Pythagorean theorem. So the Babylonians knew of the Pythagorean theorem. And so, maybe it should be called like the Babylonian theorem or something. And also, they knew much about Pythagorean triples. So what are Pythagorean triples? So Pythagorean triples are numbers a, b, and c such that a squared plus b squared is equal to c squared. Okay, so a statement, of course, about Pythagorean triples is that if you have a right triangle, of course, then the side lengths of that right triangle are Pythagorean triples. Conversely, if you have a set of Pythagorean triples, you can construct a right triangle having those as its side lengths. Okay, so there's a one-to-one correspondence between Pythagorean triples and right triangles that you can write down having those as the side lengths. Okay, so what did they know about Pythagorean triples? So there's a tablet called Plimpton 322. Is that right? Plimpton 322. Let me check. Yes, that's right. So Plimpton 322. This is from 1900 to 1600 BC. Okay. And what this says is the following. So suppose. So this is the name of a tablet, I should say. This is a tablet, Plimpton 322. So there's a fact on this tablet that says, written in modern notation, suppose U and V are relatively prime positive integers. Now, what does that mean? What does relatively prime positive integers mean? This means that it means that their GCD is 1. It means their greatest common divisor is 1. Okay, so this means, i.e., their greatest common divisor is 1. Okay, so what are some examples of relatively prime positive integers? So if you take two prime numbers, then those are relatively prime. And if you, of course, they don't have to be. That's why we use the word relatively prime, because they're prime relative to one another. So for instance, if I take, say, 15, right? And so if I take 15 and, let's take 15 and 14, right? Those are relatively prime. So, you can list the factors of 14 are 1, 2, 7, and 14. The factors of 15 are 1, 3, 5, and 15. And so their common, right, their greatest common divisor is 1 because it's the only common divisor. Okay, they don't have any other common divisors. Okay, so relatively prime positive integers U and V. Assume that not both are odd. right, that not both are odd. Okay, so maybe one is odd, but not both. All right, and without loss of generality, we can assume that U is greater than V. Okay, then, if A is defined to be 2 times UV, B is defined to be U squared minus V squared, and C is defined to be U squared plus V squared, then the GCD of these three, A, B, and C, is 1. So A, B, and C defined in this way have common, or have greatest common divisor 1, and A squared plus B squared is equal to C squared. Okay. So this is pretty impressive, right? That they knew this, and this is a very nice. In fact, if you take Math 406 here at UMD, which is the number theory course, this very fact is one of the things that you will do early in the course. Okay, early in the course when discussing Pythagorean triples, this is one of the first things you mention. And so, you know, this was known to Babylonians. In fact, Babylonians in the same tablet gave an example. So they gave an example that used this. Okay, so what are the examples of a Pythagorean triple generated in this way? The examples are 13,500, 12,709, and 18,541. So this is given on the same tablet. This occurs when you pick U equal to 125, and if you pick V equal to 54. Yeah. Okay. And so you can check that 13,500 squared plus 12,709 squared is equal to 18,541 squared. Okay. So again, what is amazing here is that this was done by the Babylonians without proof, so they knew this from empirically from a bunch of examples, and so you could make a philosophical argument for it is clear that they understood this principle. Even if they didn't provide a proof for it, so does it matter? And I'm going to, hopefully put forward the argument that it does matter in some ways, that the notion of a proof exists, because as you'll see, there's a ton of advancement that happens, and arguably it happens because of the notion of rigorous proof. Okay, this is kind of the source from where a lot of this stuff sprouts. So I will say the converse of this is also true. So that is, if you take A, B, and C that are relatively prime positive integers and take, say, A even, then and you take them such that they are a Pythagorean triple, so that A squared plus B squared is equal to C squared, then you can find relatively prime positive integers U and V that are not both odd, such that A is 2uv, B is U squared minus V squared, and C is U squared plus V squared. And the Babylonians probably knew this, but there's not too much direct evidence for that. This fact was known by a mathematician we'll talk about later, Diaphantus of Alexandria, which was in 250 AD, so about 2,000 years, a little bit more than 2,000 years past this. But actually, this rigorously wasn't written down for the first time. Even Diaphantus did all this in terms of special cases. The converse of this was not actually recognized. Actually, even this wasn't rigorously proven until the 1700s. 1738 is what's listed here. Yeah. So the proof of the converse was done for the first time in 1738. And so That's that. One last thing. I know that I said that this would be the last thing. So the Babylonians also used 3 1/8 as an approximation for pi, which isn't too bad. In some Babylonian writings, it seems like they were happy to use 3 as an approximation, and so the textbook gives an example of there's a verse in the Old Testament of the Bible that seems to indicate that pi is 3, which is the following. I'll just read directly here. So yeah, this is 1 Kings 7:23-24. So he, Hiram of Tyre, is who it's referring to, made the basin of cast metal, 10 cubits from rim to rim, circular in shape and 5 cubits high. A cord 30 cubits long gave the measurement of its girth. Under its rim and completely encircling it were gourds. They went around the basin over a length of 30 cubits. So it's implying that the diameter is 10 cubits and the circumference is 30. So that is implying that the circular basin has ratio of its circumference to diameter of 3, so that pi is 3. Of course, there's a little bit of an assumption there that the basin in question is actually circular. It just says round in the translation, so it could be that maybe it was like hexagonal or something. That's the joke that was made in the textbook. Anyway, okay, so moving on. The dawn of Greek math. All right, so this is important. This is important because we are going to spend a ridiculous amount of time. Well, it's not ridiculous, but maybe I should say a large amount of time discussing Greek mathematics. And there's a very good reason for that. And it's because the Greeks basically caught lightning in a bottle in their formulation of the foundations of math and did such a good job with this approach that it basically wasn't bettered or replicated. There were some pockets in the intervening years before the Renaissance, but Greek mathematics that was done thousands of years ago was essentially not bettered. Starting in like the 2nd century AD-ish, roughly, there was a gap where Greek mathematics was essentially not improved upon in a significant way until the Renaissance. So there was a gap of like 1,200 years where Greek mathematics was king and essentially not improved upon at all. Now, again, there's some directions that, and we'll talk about this, of course, when we get there. There are some ways in which Greek mathematics were improved upon in those years, but the results were disjointed, and they weren't. There wasn't a huge reimagining or huge improvement until much later. So Greek mathematics has, I can't possibly overstate the influence of ancient Greek mathematicians on the structure of math, and not just math, but the sciences in general, as we'll see. So this textbook is named for Thales of Miletus. Okay, which is one of the 7 sages of Athens. So this is approximately 600 BC. What is the run-up, right? What was going on before? So, of course, when we talk about Greek mathematicians, as I'll stress over and over again, in the ancient world, when we say Greek, we didn't literally mean living in mainland Greece, right? Because there were Greek colonists all over the Eastern Mediterranean, all over. There were all kinds of Greek colonial city-states in Anatolia, right, modern-day Turkey. So there were Greek colonies and Greek city-states all over the Eastern Mediterranean, all over Italy as well. So when we say Greek, we are talking about all of those things. Also later, there's the Greek city of Alexandria in Egypt, where a ton of, basically the tail end of Greek mathematics all occurred there. and so that later became the absolute center of Greek mathematics. But as we'll talk about, a lot of the Greek mathematicians were not actually based in mainland Greece. In fact, many of the high impact ones were not. Archimedes, so Archimedes was from Syracuse. Archimedes lived in Sicily. Archimedes actually lived during the Second Punic War, and was actually killed during Marcellus's siege of Syracuse. And I'll talk about all of that. So that was in the Second Punic War. It was about 214 BC or 212 BC. Basically, the beginnings, the early rumblings of Greek math began from some of the Anatolian Greek city-states. You had Greeks move from those in modern-day Western Turkey, some of those city-states. You had Greeks moving around both to Italy, back to mainland Greece, all over, bringing all kinds of ideas. And so there was a ton of transfer in that, of course, both from places where the Babylonian ideas would have been more popular or more pronounced, I guess, especially some of those Ionian city-states. But actually, the story supposedly is that Thales visited Egypt and brought back knowledge of geometry from Egypt to Athens. And so Thales supposedly brought back geometry from Egypt. Okay, so this is what was written of Thales. Of course, not a whole lot is known about Thales. There's a few results that are attributed to him. There's a funny story. One is that he was a very typical absent-minded professor, and apparently was, so involved in considering geometric problems that he wasn't paying attention to where he was walking, and he fell into a well. So this is a story that I believe Plato told the story about Thales falling into a well because he wasn't paying attention to where he was going, and had to be rescued. There was also a story that he predicted a solar eclipse in 585 BC. So, the possibility of him using Babylonian observations to do this was something that others had mentioned. So the things that he is known, the list of things that he's known for. So he is known for, well, maybe I should get more. So Thales list. What is he known for? So from geometry, a circle is bisected by a diameter of the circle. Okay. So, second thing, the base angles of an isosceles triangle are congruent. Okay. Next, when two lines intersect, the vertical angles formed are congruent. So vertical angles, if you recall that terminology, the vertical angles formed are congruent. Okay, so quick demonstration of that. All right, vertical angles would be these two, form a pair of vertical angles. And this pair is another pair of vertical angles. Okay, so vertical angles are congruent. He was the first to show this. Next, angle side. So the angle side congruence theorem for showing that two triangles are congruent. And lastly, probably the most important contribution and the thing that bears his name when talking about it in geometry is the Thales Theorem. Okay, the Thales Theorem, and I'll show you a picture of it here in a second. So what does the Thales Theorem say? So the angle subtended by a diameter of a circle is a right angle Okay. What does that mean? It means if you have 3 points, so maybe I'll start class with this actually on Wednesday, so I'll wait and show you a picture then. But it's the angle subtended by the diameter of a circle is a right angle. Actually, I'm going to give another description of Thales' theorem involving its relationship to the ratio of sides when you have a transverse cutting through the middle of a triangle. So anyway, this is a list. Now, was Thales the first to notice these facts? Absolutely not. In fact, they were probably known to Egyptians and probably known to Babylonians as well. But the main key distinguishing feature and the reason why he gets credit for this list is that he was the first to prove that. He was the first to prove all of these properties. And this started the drift towards the Greeks proving things. And this was definitely different from those that preceded them. The Greeks were the first to prove results. Okay, and so this had a huge impact because proving a result led to a huge amount of understanding. It meant that understanding in terms of examples and special cases is one thing, but in many cases it's not always possible to see what's going on in a special case in a particular example. Whereas to prove something, typically what is required is greater understanding of generally what's happening. Now, we'll get into a lot of more philosophical questions about proving versus like more like empirical understanding. But anyway, that's for next time since I'm out of time now. So I will see you all on Wednesday. I still didn't post homework. I'll do that soon. Like I said, it'll just be a few quick questions. Might ask you to write a number or a fraction in sexagesimal and or Babylonian notation. But anyway, I will see you all on Wednesday.